Good morning, ladies and gentlemen, and thank you very much for giving me the opportunity to talk about what we are doing, across the pond. And I guess Canada enjoys a special status of being, half European, half American kind of thing when it comes to space projects. My name is Freddy Pranajaya. I'm from the Spaceflight Lab at the University of Toronto Institute for Aerospace Studies, and today I will talk about a little bit about us, where we come from, the missions that we have currently, missions that are coming up, and a little bit on the technology that goes into those missions, and I'll conclude briefly after that. I must apologize that I have to run immediately after the presentation. We can have some Q&A after that, but because I'm catching my flight at 3 o'clock in the afternoon to return to Toronto. But we can always continue via email if necessary. A little bit of background about us. We actually have a complete end-to-end capability at the university. We do anything from mission design down to the hardware design themselves, manufacture them, test them, do the assembly and verification, making sure that all of the parameters are met. And then we procure the launch, we manage the launch campaign, we do the launch and early orbit operations, commission, and as well as operations of the spacecraft themselves. We try to develop actually high performance missions using these little satellites anywhere from the 100 kilogram microsat class or down to a nanosat class up to 20 kilogram. Fairly similar to the amateur world, we adopt this microspace approach in which we just do or make the spacecraft do what it needs to do and nothing else. And by doing it that way, we can achieve the goal and also save costs at the same time. Perhaps one of the key things, as was discussed in the last presentation, one of the most difficult thing in this endeavor is actually getting the launch. So we chose to actually manage and get the launch ourselves. That way, we can actually ensure that we can get into orbit in the fastest time possible. And I have some examples in regards to that. Sorry. We have about 15 people, professional. I'm one of them. In addition to that, because we are part of the university, we actually have master's students and a couple of PhD students as part of our group. And they're basically, and this is where we come in the education for these future engineers in the industry. We actually have them assign a task within each mission. And if their design turns out to be brilliant, they actually fly in space. And in some cases, we retain them after their masters are done as the staff. If things doesn't work out, then we change the assignment and just we could keep on trying until they succeed with their masters as part of our lab. In addition to all of this, we actually operate a station network currently comprising of 4 stations. The main one in Toronto, we have a UHF uplink, S-band uplink, and S-band downlink. We have Ottawa, which is we have a loaned 9.1 meter dish from our defense folks. But that's only for downlink only, for high-speed downlink. In that case, uplink will be from Toronto. Both Vancouver and Vienna actually have a duplicate of what we have in Toronto, namely the 2.1 meter dish for S-band downlink and an S-band uplink. And we're in the process of actually rolling out 2 additional stations in Northern Europe for a few of our missions. This is the microsat that actually start the lab. It's a 53 kilogram. The pictures is a bit distorted because of the wide angle lens, but basically this is about the size of your suitcase, like so. Went out in June 2003 on rocket and was only supposed to live for about a year, but currently it still works after it's 6 years and generates a whole bunch of data and makes everybody's happy, especially our CSA and our other funding agencies. Our responsibility in this case, we built the OBC, comm system structure and thermal, and also manage the testing as well as the operations following that. The payload is actually a 15 centimeter telescope. As you can see down here, telescope with a periscope mirror and then basic stairs to the back under normal operation. This side, which is you cannot see, actually faces the sun and maintains stare towards deep space to study dim lights. We're actually doing a follow-up mission to this, which with nanosats, about a 7-kilogram nanosatellite, and I'll get into that in a bit later. This is a nanosatellite quite similar to Delphi C3 in size, a 3U CubeSat, slightly heavier though at 3.5 kilogram, funded by our defense people, Space Agency, Ontario, MDA, and as well as one of our national education agency. It went up in 2008 in April, so it's been up there for about 450 days or so. Again, original lifetime is only about 1 year, but it continued to perform very well. Some of the achievement that we were able to complete with this mission is that we are able to demonstrate the 1 Mbps downlink from a small S-band with 500 milliwatt output, and that actually goes down to a 2.1 meter dish in our station. But we all operate regularly at only 256. So the 1 Mbps is only an experimental thing that we have now proven, and then for the next mission we're actually looking into putting that up with the same transmitter unit, maybe up to 2 megabit or something like that, depending. We'll see. And I believe we have the first nanosat that can actually point actively towards nadir, so nadir pointing nanosats with 1 or 2 degree accuracy, which is actually quite useful for the other aspect of the mission itself. And we have a GPS receiver and also liquid propulsion system. This one is actually intended not only as a technology demonstrator to demonstrate all of the technology, but also as a science platform. We carry atmospheric sciences experiments. There's 3 actually, and I'll get into that a little bit more after this slide. But going back a little bit on the bus itself, we have our own OS, the transmitter I've discussed. We have the reaction wheel that actually allow us to have the accurate nadir pointing capability. The propulsion system that we believe actually get something close to a theoretical limit in terms of its performance in orbit, and as well as the GPS receiver, which is as a Canadian GPS receiver, so we have no ITAR restriction in that matter. And with these results over here, we can see how the rotation rate of the body itself changes as we speed up or as we control the speed. You know, at this as we speed up and as we let the wind spins down, we can actually see that change affected on the body roll. We are able to successfully prove that it actually damp its natural roll in preparation for going into the different ACS pointing modes, and also our ability to actually align ourselves to the orbit normal. Again, that's one of the steps that's required before we can actually enter into the fine pointing, nadir pointing modes. And down here, we actually are able to correlate our GPS measurements with the NORAD TLE observations. So we're still going strong. The 3 experiments that I mentioned before, that is as part of this nanosats, actually one is actually a fairly small spectrometer, perhaps about the size of a deck of your name cards. Quite small, made by York University, and it's intended to study greenhouse gases. In addition to that, we are actually using our GPS receiver to do atmospheric occultation studies for the University of Calgary. And as well, we carry another experiment from University of Toronto that studies anti-atomic oxygen coding. And obviously, we continue with everything else, extended on-orbit operations. We'll look into how we can improve our protocols to allow us to pump down more data, fine-tuning our nadir pointing algorithms, and so on and so forth. So far so good.
Can I ask what is anti-velocity?
Oh, sorry?
Can I ask what is anti-velocity?
Oh, velocity would be as you go, and anti-velocity basically just yeah, right. Yeah, we're actually finding out that with the GPS, we had intended for it to point the antenna towards the velocity, and then we try anti-velocity, and actually we find the best way is actually to hold it up slightly.
I didn't mean to slow down your presentation.
Oh, no, it's okay. That's okay. Okay. This is since CanX2, we think that we need slightly bigger bus, so we can have more power, not too much, but just slightly more. and also more payload space. So we move up to a 20 centimeter by 20 by 20 bus size, which is something like this. This is we call the GNB, or for a generic nanosatellite bus form factor. So basically this 20, 20, and by 20 as well. Something that's quite different with this bus is that now we also built our own deployment system, whereas before it is based on the CubeSat standard, whereby everything has to be folded and tucked in inside the box. But with our separate system, which we call the XPOT, it's actually a family of separate systems. We now can actually have all of these fixed antennas. This one here is NTS is actually stands for Nanosatellite Tracking of Ships. It's a mission that we built for ComDev out in Cambridge, Ontario, and it's intended to detect ship traffic, commercial ship traffic. Each ships above a certain class are required by the International Maritime Organization to carry a transponder. So those transponders actually intended to be a self-managed cluster of things about roughly 50 kilometers across. So it's never intended to operate all the way up to 635 kilometers up in space. But ComDev come up with a brilliant idea of this receiver, and they need a bus. So they came to us and they asked, can you actually build this? And we said yes. We actually closed this mission in about 6 months from contract sign until a delivery to the launch site, and for actually a very reasonable amount of fun. As what you see here is actually the Vhf antenna. It's fixed. The last thing that we want to worry about is whether your antenna deploys correctly in space or not, because during our tests we've seen sometimes we have the quad canted thing and the other one is slightly lower, and we just, if we can, we'll like to avoid that. So we fixed that, and we also fixed our UHF uplink antennas. And you can see that our S-band is right here. Everything is ended, so we maintain a omnidirectional coverage. So even though the bus itself is only 20 centimeters, we actually the entire spacecraft is actually about 80 centimeters long, and we're about about that far away from the inside of the fairing on the launch vehicle. It's done fairly simply. It's only stabilized passively by magnetics. So as I mentioned, we actually delivered the spacecraft within 7 months. And it launches in month 7, and we did the first observation within 10 days. It takes a little bit longer because we're actually sharing the station with CanX2 at the time, so we have to half and half on that. But basically, this illustration shows the ships that NTS was able to track throughout the world. It's really quite a testament on not only the performance of the receiver itself that ComDev has built, but also the ability of what a nanosat like this can actually be used. We believe this might actually be the first operational AIS mission ever, regardless of the size of the spacecraft that they have. There's a big thing with the military now saying about response to space, and actually we did that. This is a good demonstration of that. And the result that we get here will be folded into a microsat mission that we're actually now doing for the government of Canada in conjunction with ComDev as well. It was supposed only to work for 3 months. Now we're about at 450 or 453, I guess, nowadays. We are able to download about 13.5 megabytes per day, so we collected about maybe 1.1 or 1.2 gigabytes so far of data. Everything is run automatically. Time take up scripts, observation is done at the right time in orbit, and then everything goes down and we put it out into the data repository server. And for this mission, we'll be rolling out a station in Denmark. This is the next one that we're building for Norwegian Defense. Excuse me. It's actually similar to NTS, except that the bus itself is actually a 3-axis stabilized bus. I apologize if I speak too fast, but if you have questions, just raise your hands. It's almost completed. I'll show you some pictures of the spacecraft later on. But the launch is intended to be at the end of sometime in the fall of this year. as part of our NLS-6 launch program. This one, and we also have a second satellite from Switzerland that is going to be joining us in that rocket. It's about 7 kilogram, again, the same thing with a 46 centimeter Vhf antenna, but instead of magnetically stabilized like NTS, this one is a full 3-axis stabilized with, I think, about 2-degree accuracy. So everything is ongoing. We expect the spacecraft to be ready by the September of 2009, and for this particular one, we'll be rolling out our 6th station in Svalbard in northern Norway. Basically, this is how it looks like. We have the two halves of the spacecraft. This part here would be the UHF with the 4 inputs, and this is the UHF high-speed downlink. This is the payload. This is that's the second tray that has the avionics. And this is when everything is put together. You can see this is the power board, and the computer system is actually right underneath it. On all of this type of spacecraft that we have, we actually carry up to 3 OBCs. One for housekeeping, one for ACS, and the other one is dedicated for the payload. And on the other side, this is the tray that you see just now. This is actually the tray that's underneath. You can see the 3 reaction wheel, the 2 battery system, and the GPS receiver. And this is with the antenna installed. A better view, and this is the spacecraft as it completes in the clean room just before we go into thermal vacuum test. You see the antenna, different design, but the same thing, 162 megahertz VHF antennas, and the 4 UHF and the S-band now has moved to this side. You can probably make out there's a small boom that contains the magnetometer. This is a spacecraft that I believe the idea originally came from Canada, but Austria, which we're collaborating closely with on the MOSE program, first come up with the fun. Whereas MOSE are intended to observe dim stars, magnitude 16 or so, or dimmer. This one is designed to observe bright stars. Similar things, looking at how the light varies over time, and from that they can the scientists can determine the star properties and age and all that. So because we're only looking at bright stars, we're okay with a very small 3 centimeter aperture, which you see here. This is actually a picture of the 2 instruments. In addition to that, we're also flying a star tracker, which is actually the second aperture that you see there. Interestingly enough, this science you cannot do from the ground because of atmospheric effects. So this is one of the ways that we can actually fold our knowledge to actually help science to move forward with something that's really inexpensive. We expect to complete this, I think, early next year, and launch would probably be coming up in late 2010 or early 2011. One other mission comprising of 2 spacecraft, CONNEX 4 and 5, that we are building for our government, that is intended to demonstrate formation flying capability out of small nanosats. And target completion again at the end of this, or next year rather, excuse me, we'll be flying a larger version of the propulsion system that we have now in orbit on CONNEX 2. Basically, in this particular mission, the spacecraft will launch together, and then after everything is fully checked out, it'll separate, and it'll first do a fore and aft type formation. And then after that, it can one will assume as a chief, and the deputy will come in and circle around from anywhere from 500 meters distance all the way to about 50 meters. And we'll be using this in conjunction with GPS technology to maintain accuracy within I think sub-meter. This is something, it's a microsat that we are building. As I mentioned, this is actually the follow-on to NTS. ComDev is the prime and will be the subcontractor for this one, supplying the technology listed there. This is we're building for the Canadian Defense and also the Space Agency. This is intended to basically monitor the ship traffic around Canada. But this is, again, an example of how we are able to leverage things that we know from nanosat into an actually full operational mission. You've seen how how we structure the spacecraft internally. Architecture-wise, because we now because we now have a little bit more volume, we can actually afford the multiple things. We can actually afford some cross-strapping. So in case something fails, and we can switch certain things around. So it's actually getting to be a more interesting architecture because of what it's capable of. And again, as you can see from NTS, something that's very simple, magnetically stabilized, but then you can also get into almost 1 arc-minute pointing accuracy with as you add things on enhanced capability onto the bus itself. Just something to show, ARM7 computers power. This is our S-band. This one, I believe, is our UHF systems. For uplink, we utilize anywhere from 434 to 450 megahertz. We do operate in the amateur radio frequency for our CANX2 and NTS for the uplink, but we coordinate all of our frequency with Industry Canada, which is the federal body that governs frequency use in Canada, and they in turn, I believe, also coordinate with ITU. For downlink, however, we operate at the science research band. We have an allocation at around 2.2 gigahertz for the 1 plus Mbps downlink. Just a picture of the direction wheel, sand sensor, and our magnetometer on the bottom there. Some of our propulsion system running, bare structure that you see on the mid-level there. We use anything from aluminum to a few different magnesium alloys depending on the requirements of the mission. And thermal control is obviously passive is nice because it's fairly simple, but we do have the capability to do active control as needed for the payload, for example. And this is actually a picture of the separation system that a family of separation system that we have now. This cluster here that you see is actually a picture from the NLS-4 cluster. This is one from Denmark, Germany, and what's the other one? Japan. This is for ours, and this export right there is actually the one that carries Delphi CO3. And these are all of the new export. You can see that as opposed to a fully enclosed design, now the 2 sides are open, and we can also add a slot on the door to carry additional appendages. A little bit about launch. As I mentioned before, we can actually match certain requirements from different mission. We actually have some flexibility in terms of choosing which launch is for which mission. And NLS nanosat launch service is typically a shared opportunity. So whenever we go up, we invite people to, if they have a spacecraft ready, to come and join us on our launches. Just a list of our previous launches. We have done 5 so far. We've signed our 6th launch contract for later this year. We're just about to sign our 7th contract for the next launch. This is actually the PSLV. You can see this is NTS with the 46 centimeter antenna going sideways. As I mentioned, it's about 10 centimeter or so away from the inside of the fairing, and all of the clusters actually sits down here. For the remainder of the spacecraft. We have 7 spacecraft on this particular launch. And I'd like to conclude with that, with something like a small nanosat, you can actually do a lot, and we've proven that so far. So far it's been good, and we continue to try to push the limit of the technology in that regard. And in doing so, we actually help to educate our students as well, and hopefully they can form the next generation of space engineers in the future. And we can do that in a cost-effective manner, but at the same time, when the mission requires it, we can also do it in a responsive manner. And yeah, I think that concludes my presentation. I'd be happy to answer some questions.
Thanks, Fred.
Thanks.
Do we have any questions for Freddie?
Freddie,
yes.
Your first AAS satellite that had magnetic stabilization.
Correct.
What kind of performance or experience did you have with the S-band downlink with that kind of stabilization?
Freddie, could you just repeat the question?
Oh,
so
yes.
That people over the web stream can hear
Oh,
what the
right.
question
Okay.
is. Sorry, thank you.
No problem. The question is with our passive ACS system with the magnets, how well does it work with our S-band downlink? Actually, it's been working very well. As I mentioned, we hit to 1 megabit per second from both NTS and CanX2, but our license only it's because we're limited by the bandwidth. So we did the experiment, but for regular operation we run at 256 kbps, and that one we've been able to run from horizon to horizon using the 9-meter dish.
Okay.
So yeah, technically I think we're accurate within 5 plus minus 5 degrees from the local magnetic field. So
Hi. Specifically, the S-band downlink
yeah.
and the ships locating around the globe.
Yes.
Are these two services open also for the radio amateurs? Is it possible from home to use them?
Repeat the question.
Oh yes. Whether the question is whether the ship locating is actually open to amateur. That part of the service is actually owned by ComDev because they actually the one that developed the receiver technology. So everything has to be done through ComDev. We provide the bus for them and the operations and the launch in support of that mission.
S-band and
2.2? Yeah, because our S-band is actually we do have we have a 2401 allocation at the amateur, but we actually run at 2.2. So that's a science research. So I'm not so sure that you can actually receive that because of the different frequency allocations. Sir.
Thank you. I wonder about the NTS and AIS
Yes.
stats. How do you separate the information from the ships? I mean, it's only 2 VHF channels. There's a multitude of ships. How
Yeah.
is it possible?
That information actually proprietary to ComDev. But so ComDev people, if you're listening over the web,
We had a question
Yeah.
for the Danish AMSAT organization
Uh-huh.
a year ago from DTU,
Yeah.
wanting to do a similar project
Yeah.
in the polar region.
Yeah.
Around
Okay.
That might be possible in the polar
Yeah.
region. But
Yeah. Well, I mean, you can. Sorry, I forgot to repeat the question. The question is how you actually extract the information given only 2 uplink channels and a whole slew of ships. With AIS, with NTS, the receiver technologies were built by ComDev, so they would have the answer to that. AMSAT-1, the receiver is built by Kongsberg in Norway, under funding from the Norwegian Defense. It is actually intended to study the ship traffic around. They have some fishery protection zones, or just in general around Norway. So that's actually their intention. But please, you can either contact ComDev. If you would like, you can email me. As I mentioned, unfortunately, I have to leave right after this. But you can email me, and I can get you in touch with both Kongsberg as well as ComDev. But we believe this is actually the performance actually pretty good, if not the best that we've seen, comparing with different AIS results that's been published. So that illustrate what a little guy like this can actually do.
So if an AMSAT organization was interested in launching a GNB-sized satellite through your services,
Yeah.
What sort of ballpark figure cost for launch?
Okay. The question is that what is the ballpark figure to cost to launch? Sorry, the cost to launch a GNB-sized spacecraft. Launch cost varies. It's because we go by the market price actually. For example, for a 1U CubeSat right now, it's about 55,000 euros to launch a single UN. But that includes the way we always done it is that we go with we provide it with the XPOT, and everybody has their own XPOT because that's just the best way it is. Not only it's safer for you, we can actually fine tune the deployment. So just optimize the injection parameters for your particular spacecraft, and also makes NORAD happy. What we know from the past, if you have a cluster, and especially if they don't know that it's actually coming, they're actually a bit unhappy because now they have to shift through everything else and try to pick everything, which one is which. But we actually coordinate not only with the LV, because LV has some limitation as far as they like to do certain things within a window of translation or something like that. So we fine-tune our deployment timing, our deployment speed, so as to meet our own internal requirements, the LV's requirements, and also NORAD's requirements. So all three are happy.
Sort them out
Yeah, like for example, with our PSLV-C9 launch, NORAD picked it up. I think in the first pass, one orbit after deployment, they can say, we see 7 different objects or something like that almost immediately. Whereas before it took us took NORAD quite some time before they can actually see individual blips.
So would that the one you price scale
Yeah.
based on mass?
Roughly speaking, yes. Yes. So for a 6 kilogram, you'll be looking at 300-ish
Okay, thank you.
euro. Kilo euro.
I'll take one last question, then we'll cut it. John.
Yeah, could a ship at sea, like a cargo ship,
Yeah.
receive this AIS data from one of your satellites, assuming they might be geostationary? Is that part of the plan? That could be beneficial to give a wider view of the other shipping in the...
Yeah, well, that's actually unfortunately with NTS we can only, because it's a limitation. We don't have much time when when ComDev comes and we need a satellite, to be in orbit 6 months from now. At first we said, are you crazy? But after a while, it's like, okay, fine, we'll do it. Because of that, we have to fly what we have on the shelf.
Yeah.
So we're actually limited in collecting only 90-second shot of a sea, of an ocean. But yes, eventually, it'll be nice, of course, if you can then do a full snapshot. But that question, I think, is best.
the benefit
best.
for ships.
Oh yeah, of course.
Our Radio Club treasurer spends his life going around the world on a cargo ship.
Oh, so you like to know where he is it?
I know where he is.
You can use APRS, John. You can use APRS.
Oh, we do. We're on HF every
Yeah.
Okay, I think we'll call that a day. I think that's okay. If you've got burning questions, Freddie's taxi leaves, I think, in about 10 minutes to go to Heathrow.
Yeah.
So you could walk with him down the corridor. Other than that, you're on the email. Do you have a card or no?
No, unfortunately, I think, but
Dave's probably got the contact.
yes.
Freddie, thanks very much. Safe journey home, and thank you for your.
Thank you again.